In our previous video, we talked about intermolecular forces, and I mentioned that those forces determine the various properties of liquids. So in this video, we're going to look at the different properties liquids have and how those are related to intermolecular forces. So there's 5 basic properties of liquids we're interested in: the boiling point, the temperature at which the liquid boils, viscosity, surface tension, vapor pressure, and the heat of vaporization. So each of these, as I mentioned before, depends on the strength of the intermolecular forces, and each of them is either going to be directly related or inversely related to those intermolecular forces. If they're directly related, that means that the stronger the intermolecular forces, the greater that particular property will be, and if they're inversely proportional, then it will be the opposite. The stronger the forces, the less that property will be. So let's start out and take a look at boiling point. The boiling point is essentially the temperature at which a liquid boils. We can see that in this boiling water, it's at 100 degrees Celsius or about 212 Fahrenheit. And so how is the boiling temperature of the liquid related to these intermolecular forces? Well, if you think about it, in order for a liquid to boil, we have to break the bonds between those molecules. So logically, the stronger the bonds between the molecules, the more energy we would imagine that it would take to break those bonds, and therefore we'd expect stronger bonds or stronger intermolecular forces to give us a higher boiling point. So the boiling point is directly proportional to the strength of the intermolecular forces. If I asked you to name a viscous liquid, you would probably come up with something like honey, or perhaps motor oil. Both of these are viscous liquids. Something that's viscous basically means that it flows slowly. Sometimes people say the liquid is thick. But viscosity is more technically a resistance to flow. So the more viscous or the higher the viscosity of a liquid, the slower it flows. Now, if we think about this on a molecular level, it makes sense. When this honey is flowing out of a container or off of this wooden spoon, the molecules in the honey are flowing past one another. And as they flow by one another, they have a tendency to stick together because there are intermolecular forces. Logically, the stronger those intermolecular forces, the more difficult it will be for those molecules to slide by one another, and the slower they are going to move. So based on that, we would assume that viscosity, like the boiling point, is directly proportional to intermolecular forces. The stronger the bonds between the molecules, the more difficult it is for them to flow past one another, and the more viscous the liquid will be. The scientific definition of surface tension is a little complicated, so I think it might be easier if we just look at some examples of surface tension in action. This is a water strider or a water bug, and you've probably seen them flitting around on the surface of water. These insects are actually denser than water, so by all rights they ought to sink, but they don't. You can see that their legs are making an indentation in the water. It's almost like the water's got a film of plastic over it, and the insect is pushing down and making a dent or an indentation in that surface, but it's not breaking through. And the reason it doesn't break through is intermolecular forces. There are attractions between the water molecules, and for the insect to break through, it has to break those bonds, and the weight of the insect simply isn't strong enough to do that. You've also certainly seen water bead up on the surface of a car. The reason the water beads up is due to surface tension. And we'll talk in a little bit about exactly why the water beads up. So surface tension, like viscosity and boiling point, is directly proportional to the strength of these intermolecular forces. If the bonds in this liquid were weaker, it would be easier for the insect to break through and it would sink. Water just happens to have very strong attractive forces because, as we learned earlier, water has hydrogen bonding. So back to our question we asked a moment ago, and that is, why does water bead up on a waxed surface? Is it because the water doesn't like wax? Or does wax repel water? And the answer is no. There's actually no such thing as repulsion when it comes to molecules. All molecules attract each other. So why is the water appearing to try to get away from the wax? Because the wax is actually attracted to the water. The key thing is how much is each thing attracted to the other. Water does like wax. There is an attraction between these water molecules and the molecules of the wax, but water loves water. Water would much rather bond with other water molecules than it would with the wax. Why does it want to do that? It's very simple. To get stronger bonds. We've talked about that earlier in the semester, and the fact that most physical and chemical changes, what drives them, what makes them happen, is that desire to get stronger bonds. Chemical compounds form because the atoms want to get stronger bonds. So the water molecules are beating up because in the droplet, all those molecules floating around inside the drop are surrounded by other water molecules. If the water spreads out on the surface, then the molecules find themselves bonding to the wax, and that's simply less satisfying. The molecules never want to give up stronger bonds to get weaker bonds in return. So, what's wrong with this picture? This is a bottle of Rain-X water repellent. Well, the problem is, as I mentioned a moment ago, molecules don't repel each other. There's no such thing as water repellent. I've always said if there were truth in advertising, these would be called water-less attractants, because that's really what they are. The chemical in here, usually a silicone, a nonpolar material, simply makes a surface less attractive to water, and therefore the water prefers the company of other water molecules. When you spray a water repellent on a fabric, you notice, oh, the water droplets bead up, and the reason is very simple. They would rather bond with each other and get stronger bonds than get the weaker bonds they would get with that water repellent, so to speak, silicone coating. Our next property is called vapor pressure. If we take a look at this diagram, at the beginning we have a container of liquid inside a sealed jar. Now the molecules of the liquid, like all liquids, will begin to evaporate. Molecules will escape from the surface of the liquid and they will move up into the air. As more and more of the molecules enter the air, some of the molecules begin to randomly bounce around and they will go back into the liquid. So in the beginning, it's a one-way trip. All the molecules are leaving the liquid. They are evaporating or vaporizing. After a time, some of the molecules begin to condense, so condensation occurs, but still vaporization is happening faster than condensation, so more and more molecules begin to build up in the air. Eventually, we get to a point where there's so many molecules of the liquid vapor in the air that they're now condensing just as fast as they're vaporizing. So we get to a point where for every molecule that leaves, another molecule returns to the liquid, and we've reached a state which is known as dynamic equilibrium. Equilibrium means balance, and so we have a balance between vaporization and condensation. The word dynamic simply means things are changing. So dynamic equilibrium basically means that there's two changes occurring, but they're happening in opposite directions at equal rates. So as you get more and more molecules of the vapor up here, it causes an increase in the pressure. There's more molecules now bouncing around inside the container, hitting the surface of that glass, And that extra pressure caused by the vapor is called the vapor pressure. So how are vapor pressure and intermolecular forces related? Well, let's think about it. If the bonds are strong in the liquid, it's going to be difficult for those molecules to escape, and so you're going to get less vapor molecules. If the bonds in the liquid are weak, they're going to escape very rapidly, and you're going to get lots of vapor molecules, and thus more pressure. So unlike the previous properties, vapor pressure and intermolecular forces are inversely proportional. The stronger the bonds in the liquid, the less vaporization you get, and the less vapor pressure you get. The last of our properties is called heat of vaporization. It's basically the energy involved in vaporizing a liquid. Do you suppose it requires energy to vaporize a liquid? Obviously it should, because when you vaporize something, you're essentially breaking bonds. And as we've said many times, breaking bonds always requires energy. So the heat of vaporization is simply the amount of energy that's required to change a liquid into a gas. Now, it doesn't necessarily have to be at the boiling point. This slide's not entirely correct, because vaporization can occur in a liquid at any temperature. Water vaporizes at room temperature when it evaporates. But in general, it's simply the amount of energy you need to convert the liquid into a gas. So, how do we suppose these two would be related? If you think about it, if the bonds in the liquid are stronger, it should take more energy to break those bonds. So we would anticipate that, like our first three properties, it's going to be directly proportional. So of the 5 properties that we studied, only the vapor pressure was inversely proportional to the intermolecular forces. The other 4 were all directly proportional. Now there's also another property that's similar to this called the heat of fusion, and fusion simply means melting. So the heat of fusion is the amount of energy required to change a liquid from a solid, a substance from a solid to a liquid. So which of these do you suppose is greater? Does it take more energy to vaporize a substance or to melt a substance? Well, for water, the heat of vaporization is 2,260 joules per gram. That's a lot of energy. So every gram of water that turns from a liquid to a gas requires 2,260 joules. So, do you suppose the heat of fusion will be higher or lower than that? Well, let's think about what's happening. When you vaporize a liquid, you're actually breaking bonds. When you melt a liquid or melt a solid, all you're doing is loosening or weakening the bond. So the question becomes very simple. What requires more energy, breaking bonds or loosening bonds? And logically, we would expect that breaking the bonds in vaporization ought to be greater, and it is. The heat of fusion for water is substantially less, about 1/7 as much. Only 335 joules are required to melt a gram of ice. 2,260 joules are needed to vaporize a gram of water. And this is true for all substances. No matter what the material is, the heat of vaporization is always going to be significantly greater than the heat of fusion. We can combine what we learned in Chapter 14 with what we talked about back in Chapter 7 when we first began to discuss energy and physical and chemical changes. This particular diagram is called a heating-cooling curve, and it shows what happens to a substance as you add energy to it or as you remove energy. So the amount of energy is increasing along this axis and the temperature is increasing on this axis. So let's suppose we started out with a solid below its melting or freezing point. This could be water, say at -20 degrees Celsius. What happens if you take an ice cube out of the freezer? And that ice cube, they're usually at about -20 degrees Celsius. The moment you begin to warm up that ice cube, what happens? Now, most people will say, oh, the ice cube begins to melt. But that is not the case. The ice cube will not melt. Ice doesn't melt till you get to its melting point of 0 degrees Celsius. So when you pull that ice cube out of the freezer, the next time you do it, feel that ice cube and you'll notice it's not wet. It's not melting. It feels dry and rough. That ice cube will not melt until its temperature reaches the melting point. So the first thing that's going to happen is the temperature of the ice is going to rise. Once it reaches the melting point, then it will begin to melt. It'll change from a solid to a liquid. So you can see below the freezing point, it's all solid. Once we get to the melting point, now the solid slowly begins to convert to liquid. Now what happens if you take that piece of ice once it's reached 0 degrees and you hit it with a blowtorch? You put a flame on that ice cube. Can you raise the temperature of that ice cube? The answer is no. You can heat the heck out of that ice cube, but it is not going to go above 0. It's going to follow this flat plateau here. The more energy you put in, the faster it's going to melt. But every 335 joules of energy you put into that ice cube is going to melt 1 more gram of ice until it's completely melted. Once it is completely melted, now that it's all liquid, if you continue adding energy to it, the liquid molecules will simply move faster and the temperature will rise until it reaches the boiling point. Once the liquid reaches the boiling point, it's going to slowly turn from a liquid to a gas. Now you can heat that liquid all you want. If you're boiling water on your stove and you think you can cook food faster by simply turning the burner on high and that water's just boiling like mad, if you put a thermometer in there, it's going to be 100 degrees. Whether it's a gentle simmering boil or a rolling boil, you can't heat it above 100 degrees Celsius, at least not with doing something special. So your food's not going to cook any faster if you boil it rapidly or you boil it gently, because the time required to cook food depends on the temperature you cook it at. And when you cook something in boiling water, it's always cooking at 100 degrees. Now, once the water is completely vaporized, if you continue adding energy, you can heat the water vapor up basically as hot as you want until you get to maybe 2,000 to 2,500 degrees Celsius. And then the energy is so great, the water molecules themselves will actually break apart into hydrogen and oxygen. Now, you take a look at this other little figure. It sort of summarizes this. So melting and freezing are basically the same process, just in reverse. So if you look on the curve here, if you go from left to right, you're melting a solid. If you go from right to left, you're freezing a liquid. Same thing is true above. We have evaporation or vaporization and condensation. So if you're moving from left to right, you are vaporizing or evaporating the liquid. Right to left, you're condensing it back into liquid water or whatever the liquid happens to be. Now, it is possible in some cases to go directly from solid all the way to gas. That particular process is called sublimation. If you've ever kept ice cubes in your freezer, sometimes you dig down in the ice tray and you find these little tiny misformed ice cubes. You know, how did I get those tiny little oddly shaped ice cubes? What's been happening is those ice cubes have been in the freezer a long time, and molecules of water have simply been breaking free directly from the surface of the ice and becoming vapor, and so the ice has essentially been vaporizing. And the opposite process is possible as well. That's what frost is. When you see frost on a cold day or after a cold night, that frost is simply vapors of water turning directly into crystals of ice. Vaporization is a general term that simply means a liquid is becoming a gas. But there's actually a couple of different ways that can happen. One way is by evaporation, and the other is boiling. So each of those has a couple of characteristics that identify it. For example, evaporation occurs over a wide range of temperatures. So a liquid can evaporate at any temperature in which it's liquid. So ice water at 0 degrees Celsius will evaporate. Boiling water will evaporate. It'll simply evaporate faster. Boiling, on the other hand, occurs at a specific temperature. For water, we say that the boiling point of water is 100 degrees Celsius. It doesn't boil at 95 or 105, it boils at 100. With evaporation, it occurs only at the surface of a liquid. So for a liquid to evaporate, molecules have to break free from the surface and escape into the air. On the other hand, boiling can occur anywhere in the liquid. So it depends on where the heat is. In a pan on your stovetop, you normally see the bubbles forming at the bottom of the pan. If you boil water in a microwave, those bubbles can form anywhere. So is the boiling point of water always 100 degrees Celsius? Well, it seems like I just said that, but like many things, they're not always as simple as they appear at the beginning. Let's take a look and see what exactly has to occur for boiling to happen. Essentially, for boiling to take place, the vapor escaping from the liquid has to be able to push the air out of the container. So the air is pushing down on the surface of the liquid with 1 atmosphere or 760 torr or whatever units you use of pressure. So the vapor of the liquid has to push up with the same amount of force. That's what we learned about earlier, called the vapor pressure. And we also learned, of course, that vapor pressure is not going to be the same at every temperature, because for molecules to escape from a liquid, they need energy. Every gram of water molecules that escape from that liquid need 2,260 joules of energy. So logically, the more energy you put in, the faster that's going to happen. So the fact is, water will not always boil at 100 degrees Celsius because atmospheric pressure is not always the same. At sea level in Stockton, the atmospheric pressure is about 1 atmosphere. At different elevations, that pressure will be different. But the overall rule is very simple. When the vapor pressure of the liquid pushing up equals the atmospheric pressure pushing down, then the liquid will boil. So if you change the atmospheric pressure, you'll change the amount of vapor pressure required to boil, and that will change the boiling point. 100 degrees Celsius we usually refer to as the normal boiling point of water. That means its boiling point at 1 atmosphere of pressure. So this graph shows the vapor pressure of water at various temperatures. And interestingly enough, you'll notice that the vapor pressure of water reaches 760 millimeters of mercury, which is 1 atmosphere, at precisely 100 degrees Celsius. That's why water normally boils at 100 degrees Celsius, because that's the temperature at which the vapor pressure of the water is equal to that atmospheric pressure pushing down on it. Now, what if we went up to Lake Tahoe? If you get up to Lake Tahoe, the atmospheric pressure is going to be less. It's only going to be about 80% of what it is in Stockton, which means it's going to take less energy to boil the water. If we look at the graph, when we get up to about 93 degrees Celsius, we reach a vapor pressure of 600 millimeters of mercury, and that's about what the pressure is in Tahoe. So water in Lake Tahoe will boil at about 93 degrees Celsius. If we reduce the pressure even further, if we were to put the water in a vacuum container and pump a lot of the air out, if we got the pressure inside our container all the way down to 25 millimeters of mercury, that water would boil at room temperature. You could hold it in your hand and it would feel completely cool. So boiling does not always mean hot. I often ask students to tell me, what's the first word that comes into your mind when I say boiling? And they normally say hot. But boiling is not a particular temperature. Boiling is a change of state. It can happen at a high temperature. It can happen at a low temperature. One thing I always find interesting in teaching chemistry is at the beginning of the semester, most students have very little knowledge about science, and so I can't get into very detailed explanations, but I always tell everybody the farther we get on into the semester, the deeper your understanding is going to be, and there's a lot of questions that we'll be able to answer in more depth, and you'll be able to understand perhaps some everyday things you've observed and never really knew why they were the way they were. So here's a few questions to think about. I always love to ask my students this one. How long does it take to cook a 3-minute egg in Lake Tahoe? Now you're probably thinking, hey, wait a minute, is that a trick question? It's probably 3 minutes. Well, I suppose it could be, but a 3-minute egg is a soft-boiled egg. So when I say a 3-minute egg, I mean an egg that has been cooked to the consistency that you would normally expect a 3-minute or soft-boiled egg to have. So we're going to make this a multiple choice question. Your possible answers are 3 minutes, less than 3 minutes, or more than 3 minutes. So take a moment and think about that. You can pause the video if you wish, and then we'll look at the answer. And the answer, of course, is more than 3 minutes. And the reason is very simple. I mentioned a little while ago that the time required to cook food depends on the temperature at which you cook it. That's why in boiling water, whether it's a gentle boil or a vigorous boil, it's still 100 degrees Celsius. It still takes the same amount of time. But in Lake Tahoe, as we just found out, water boils at only 93 degrees. So we're cooking our egg at a lower temperature, and that means it's going to take longer to get that done. I'm sure all of you are familiar that when you cook food in your oven, the higher you turn the temperature in the oven, the faster the particular food is done. All right, here's another one that you've probably noticed. You get out of a swimming pool on a hot summer day in Stockton, yet you feel a chill. You're cold. And well, how in the world can we feel cold when we get out of a pool on a 95-degree day? And the answer is, it has to do with heat of vaporization. When you get out of that pool, you're wet, and the water on your skin begins to evaporate. And of course, as we learned a little while ago, every gram of water that evaporates from your skin needs 2,260 joules of energy. And where do you suppose it's getting all of that energy from? That's right, it's getting it from you. It's taking that energy out of your body, and that's what's making you feel colder. That's why they often put wet cloths on people when they have a fever. They'll put it on their forehead, and that evaporating water will help cool the person down. Now, a lot of people in Stockton have swamp coolers. I've seen a lot of people with those on their roofs. Maybe some of you have those. A swamp cooler is sort of like an air conditioner, only it's much simpler. All it really is a belt that goes around through a tub of water, and the water evaporates off of the belt, and of course as the water evaporates, it takes energy from the belt, and the belt gets colder. So why don't swamp coolers work in swamps? They only use them in dry climates. And the answer is very simple. It goes back to our old buddy, dynamic equilibrium. Dynamic equilibrium, again, means that processes can happen in two directions. If you're in Louisiana in the summertime and it is incredibly humid, maybe the humidity is 100%. At 100% humidity, the air is saturated with water molecules. So every time a water molecule evaporates from your skin or from the swamp cooler, another water molecule condenses. So a gram of water molecules leave, and they take with it 2,260 joules of energy, yay. But then another gram of water molecules from the air, they condense back down, and they release 2,260 joules of energy, so you have ended up gaining nothing. So swamp coolers really only work in dry climates. In Arizona, very common. Almost everyone has a swamp cooler because it's a hot, dry climate. And finally, one last question. Why does food cook faster in a pressure cooker? Well, the whole key behind a pressure cooker is pressure. I mean, inside a pressure cooker, it's sealed so that when the water begins to boil, all of that water vapor increases the pressure inside of the pressure cooker. And as we learned a little bit ago, the boiling point of water depends on the external pressure it's pushing against. Inside that pressure cooker, instead of the usual 760 millimeters of mercury, the pressure might be 1200. At that higher pressure, it's harder for the water to boil, so perhaps you have to heat it up to, say, 120 degrees Celsius. And at 120 degrees Celsius, now the water will boil again, but your food is cooking at a much higher temperature. Rule of thumb for cooking, or for chemical reactions in general, is every 10 degrees Celsius that you increase the temperature, it cuts in half the time needed to cook the food. So pressure cookers are very convenient for cooking foods much faster.